Go.
Hello!
That's it. Hello, Mr. Eric, Mr. Ryan. How are you today? Okay, so today we are going to talk about the concept of dynamic programming.
I already know dynamics.
Are you sure?
Yeah, it's one piano, one instrument.
Dynamic programming.
It's about how loud or like 4K,
Okay,
4K is.
It's not just exactly the same, but
Piano.
dynamic programming. So what's dynamic? What's the dynamic? What's the opposite of dynamic? What's dynamic? What does it mean?
Something like sound.
Sound. Now, dynamic means, and the opposite will be static.
Static.
Yeah, static dynamic. Yeah, dynamic programming. So it's not easy to understand what it means from just reading these two words. So, but I give you one example. Yeah. So it's like a way we store the intermediate result. There's nothing there. Don't look at it. So, for example, if I give you 5 apples, yeah, you have 5 apples.
I'll eat it all.
No. And then I later, like 5 seconds later, I give you one more. So how many of them altogether?
6.
That's dynamic programming. Because you don't count from the start. Yeah, you already know what you got is 5, and you are given one more. So you just reuse the result of the 5. You're not counting it from start 1, 2, 3, 4, 5. Does it make sense?
Yeah.
So you tell me what it is, okay? Fn equals Fn minus 1 plus Fn minus 2. What does it mean? This item is the sum of the previous 2 items. 1, 1, 2, 3, 5, 8, 13. What's this?
I think it begins with F. It's something.
Fibonacci numbers.
Fibonacci.
Yeah. The sum of.
I will still remember.
You remember? Yeah.
1, 1, 2, 3, 4.
So how do we implement this?
13.
Do you still remember?
Then 21 is a number.
Look. So look.
Fibonacci number.
Define Fn. Okay.
How long?
If n equals.
Is it supposed to be like a...
Yeah. That's all. If n equals 0 or n equals 1, return the first 2 items. Let's say return.
X.
Let's
Zero,
make it 0, 1, 1, 2. Okay, so return n, yeah? And n return Fn plus Fn minus 1 plus Fn minus 2. Am I?
Minus 2.
Okay.
Yeah.
So this is recursion, yeah? But do you see the problem of this? Eric, do you see the problem?
What?
The problem of this code. Do you see it?
I see the whole thing.
Yeah, look. I showed you this before, right? Remember, if I want to calculate F4. So F4, I need to know F3, yeah? And F2, right? Yes? Alright? And in order to calculate F3, what should I do?
I'm not a Fibonacci number.
Okay.
I'm a Fibonacci
And then
number.
F2, I need to remember what? I need to calculate what? F1 and F0, yeah?
Yeah.
And F1 and F0 we already know, right?
Yeah.
Look, do you see this problem? F2, I need to calculate F1 and F0. So do you see the problem, Eric? Do you see the problem from this? If I want to calculate F4, Ryan, I need to calculate F3 and F2. And in order to calculate F3, I need to calculate F2 and F1. In order to calculate F2, I need to calculate F1 and F0. In order to calculate F2, I need to calculate F1 and 0. Do you see the problem? Do you see the problem? Ryan? Come on, sure, it's right there. What's the problem with this?
It's like a binary tree.
Yeah, it's the binary tree, but look, I want to calculate F4, but using this code, yeah, recursion, I need to calculate F3 and F2. Yeah, there are 2 function calls. In order to calculate F3, I need to calculate F2 and F1. In order to calculate F2, I need to calculate F1 and F2.
So long.
Yeah, and F1 and F1. Okay, F0. And in order to calculate F2, I need to calculate F1 and 0. Do you see the problem? Do you see the problem? It's right there. What's the problem? What's the problem of this
It's
bit?
not symmetrical.
No. What? I give you a hint. It's something that has been calculated more than once. Which one?
1 and 0 and 2.
Yeah, you see. Because look, F2. I want to calculate F2, and then here I also again. And can you imagine? There are lots of things coming on. Yeah. If F5 and then you find F3 somewhere, you calculate again and again, and this grows exponential. Do you get it? Do you see it? Yeah. Do you see the problem? Yeah. Because I want to calculate F3 and then I need to calculate F2. But somehow F2 is being calculated here, and I have, no matter how complex is F2, I need to do it again. Yeah. So it's like I give you 5 apples. I give you one more. You recalculate it. You count it again. 1 apple, 2 apple, 3 apple, 4 apple, 5 apple, and then you now know 6 apple. And now you have 6 apple. I give you one more apple. You get 1, 2, 3, 4, 5, 6, 7. You're not doing that right?
You could just go next number by before.
Yeah, that's right. So what's the technology here? So you are not counting it from the beginning because it takes time, and you calculated the thing you already know, right? It's like you already know there are 5 apples, and then you're counting it again. Yeah, because you're not remembering. Okay, so how do we remembering? I give you a hint. It's a word. I talk about that a lot. What kind of data structure are we using to remember? Yes, set is kind of notebook, textbook. Okay, so look, the problem of this is that we are not remembering the intermediate results, right? If we remembering this, if we calculate the first time we calculate F2, yeah, we save this into a notebook, and then when we come here, F2, then now we know already F2, right? So we don't need to calculate again, right? We can just get the value from the notebook. Am I right?
Yeah.
So that's dynamic programming. Do you get it?
Yeah.
So that's recursion, but with the notebook. Actually, it's not notebook, but notebook is for your understanding. In computer science, it's called this memoization. What does it mean? Memoization. Yeah, recursion with the memoization. So how do we do this? What does this mean?
Mo.
What does this mean? What does this mean? Look, we can do this. Put a notebook. Yeah.
Notebook.
Equals. We can just look. Yeah. Yeah. Notebook. Yeah. And now. Okay. Look. I do it right here. Okay. Return fn minus 1 plus fn minus 2. Okay. So now I want to put it. Look it here. So look. If n in notebook, return notebook n. And now I need to say value equals, and then what should I do? I should put it in the notebook, right? Yeah, so notebook n equals what?
Equals.
What's the value here? Value. And return what?
Return.
What are we calculating here? Ryan, any thoughts?
F.
What's F? F is the function name. Come on.
Return. Value.
Exactly.
I was
Because
about to say that.
look, this is the value. We put it in the notebook. Do you get it? And then this bit is to check if this n is in the notebook. If it's in the notebook, it means we have calculated it before, right? So we don't calculate. We just return the value. Okay?
Yup.
Okay. So this whole thing, we don't need to do that. That's one magic. Erase this. Erase this. Erase this. Just get back to the beginning, okay? Return, yeah? Yeah? Return this, yeah? This is a recursion, yeah? all we have to do is add something here. Add LRU, this reasonable unit cache. And then we can specify a size, max size equals none. So this is just to ask computer to cache this function if possible. So the computer, when we recursively call this F2, for example, F2, yeah? Then if we check if it's already calculated before, you won't continue. You will just return the value. Got it?
Mm.
So
I can't remember that.
that's okay. That's okay. That's okay. But you can remember the notebook thing. Yeah, it's the same thing. LRU cache. Cache. You know what's cache?
Cash. Money.
No, cache, not cash. This is cache. Cache. Cache.
I
What's
don't know.
cache? It's like what's cache? It's like it's like something you want to use frequently, and then you don't need to go and do it again. You can just put it on some place that you can fetch it quickly. Cache. Okay. A storage that stores the intermediate in the frequently used value, like notebook. Yeah. A storage. Okay. So look, 5 apples. Yeah. Then you know in your memory, you know there's a place called you now have 5 apples. And the next time you're given 1 apple, you will ask yourself, how many apples do I have right now? I have 5 apples, and then I can just say, okay, I get these 5 apples, and then plus 1, so I will have 6 apples. And then you update in the cache, and then it will become 6. And next time you're given 1 apple, and you go and ask the cache, how many apples do I have now? 6? Yeah? And then 6 plus 1 equals 7. And then you go back to update the cache. If you don't have this cache, what happens? You need to do this heavy work. You need to count apples from 1, 2, 3, 4, 5, 7. Imagine you are given 1,000,000 apples. Then it will take time, right? But if you have a cache, a place, memory, to tell you how many apples, do you need to go there? No, right? Yeah, and this will be very fast, yeah? Yeah, a fast storage, a fast retrieve storage cache. So look, this is recursion. Recursion with cache, minimization, yeah? Minimization, the thing I talk about, minimization is called what? It's called what? What are we talking about today? The what? The two words?
Something very cake.
Dynamic programming or DP. Dynamic programming. This is very advanced technology, okay? Advanced algorithm, dynamic programming. Got it?
Yeah.
Okay. So can you write the Fibonacci number? Okay, just one more time, okay? I'll write it one more time. You tell me what? Yeah. Look.
0. What's D?
Oh, look, dynamic programming, you can write it, look this way, yeah, define Fn, yeah? Okay, let's write the notebook, notebook version, okay?
Yay!
Okay, look, if n smaller equals 1, return what?
Return.
N, right?
Yeah.
And then if n in notebook, what should we return? Return what? Notebook n, yeah?
Yeah.
Okay, and the value equals what? F what?
F. F. -1.
Plus.
F. And -2.
Okay, and then what should we do now?
Yeah.
What should we do now? Notebook n equals what?
Notebook n equals n plus 1. Value.
Value, yes, and then return what?
Value.
Value. So this, look, this is Fn, yeah? Yeah, this is Fn. And then I need to go top down, Fn minus 1 and Fn minus 2. And then this will be Fn minus 2, Fn minus 3, yeah? Look, top down. Yeah? So this is dynamic programming. Again, we call it top down because look, the way you are calculating is from top to down, yeah? A tree, top down, yeah? Top down dynamic programming. And it's usually implemented using recursion with the notebook, with the memorization. It's called recursion with the memorization. This is very important. If you don't memorize the results, the values, it's not the core dynamic programming. Yeah? The beauty of dynamic programming is that you don't calculate those intermediate values over and over again. So let's speed up. Yeah? If you're calculating these F4, F2 again and again and again, it's going to take forever. It's going to take exponential time. But with this memorization, for Fn, how many times you just have to calculate it?
What?
N, because for each value, let's say F10. So I just need to calculate F9, F8, F7, till F1, F0. All these numbers only calculate once, right? Yes? Why is that? Because if it's calculated, I can put it in the notebook. And next time you want it, I just get it, right? Yes? So look, recursion with the memorization, dynamic programming, the complexity for the Fibonacci number is O1. O-N, because they are calculating time. But without the memorization, without that bit,
A1.
it's what? It's O1.
N square?
Not quite close. It's look each
N times N.
no look
square.
each one you spawn two possibility. Each one you spawn two possibility.
N cubic.
2 to the power of n exponential. Got it? Yeah? Because at each one you have 2, spawn 2. Each one you have 2. Do you get it? So it's exponential. Look, O2n and On, which is better?
On.
Yeah, of course. Because look, On is this. O2n is what? Yeah? So when n is 10, 2n is 1024, but 10, On is just 10. Yeah? You got it? Yeah? This 2n graph is a lot higher, right? This is the On. Okay? Got it? Yes? Okay, so this top-down dynamic programming, we also can calculate from bottom up by dynamic programming. Look, if we calculate from this direction, yeah, we can calculate F0 first, F1, and then we can calculate F2, F3, F4, F5 until F10. Got it? So do you see Fibonacci number F10 top down? We want to calculate F10. Then we calculate F8 and F9. And in order to calculate F9, I need to calculate F8 and F7. That's top down, right? It's implemented by recursion with memorization. You got it this part, yeah?
Yeah.
For that bottom up, we calculate up. I want to calculate F10, but let's calculate F0, F1 first. F0, F1, and then I can calculate F2. Yeah? F1 and F2, I can calculate F3. Got it? Yeah? So how do we do this? Look, we can just do this. Yeah, look. F, let's just call the first one F0 and F1, okay? Equals 0, 1, okay? Yeah? Then for I in range I, okay? Range N. And F0, F1 equals what? Look, F0 will become F1, right? Yes? Yeah? Look, 1, 1, 2, 3. Okay, so this is F0, this is F1. So the next iteration will be F0, F1. Yeah. So F0 will become the F1, and F1 will become F0 plus S1, right? Yes. So that will be F0 plus F1. Got it? Yes. So after n direction, so look, if F3, if you want to calculate F3, so this is 3 times. So 1, 2, 3. So we just return this number, which is return F1, right? Got it? So do you get it? If I want to calculate F10, F0, F1, and I can calculate look, F10, 5, 8, 13, 21. Okay, so look, this is F0, F1, yeah? And the next one is I move here. I can calculate this. Yeah. I move here, move here, move here, move here, move here. Each one f0 equals f1. F1 will be f0 plus f1. Look, f0, f1. F0 is the f1 will become the new f0, and then the new f1 will become the old f0 and f1. Right? Got it?
Yeah.
Okay. So this is called the bottom up. It's also dynamic programming. This is also dynamic programming. Why is that? Because it reuse the values, intermediate value. Yeah. You see for f2, you only calculate once, right? It doesn't calculate again and again, right? So the complexity is also O what?
N.
O n. Okay. So do you get it? So how many kind of dynamic programming we have?
3.
Two, three? Why is it?
Two.
Two. What are those?
The dynamic. One with the notebook.
Yeah, that's called
One is with memorization.
it's called top down, right?
Yeah.
And this one is what? Bottom up, right?
Yeah.
Why are we using the dynamic programming to what? What's the advantage?
The Fibonacci numbers.
No.
Memorization.
Yeah, to
remember.
avoid to calculate the same value again and again. Okay?
Yeah.
So this is to reuse the thing to avoid calculating intermediate results over and over again. Because we calculate once, we remember it, we don't come back and calculate it again. This is the advantage. Okay? Okay, that's it for today. Thank you.
Bye. 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 Bye.
Bye bye.